Hey everybody, today I'm with Dr. Nicholas Starvaggi. He's one of my good friends, and we were lab mates together when we did our PhD. He's going to talk to us today about his experience with his PhD and the research he was doing and the research he does now, and kind of how he feels about where science is going and stuff like that. Nicholas, thanks for being here with me, man. Glad to see you.
Yep, thanks for having me. This is really exciting to be here and talk about this stuff.
Well, I'm glad. So obviously I just introduced you to everyone, but can you give us just a little background on yourself? Like obviously. Well, actually, if anyone didn't know, I did my PhD at A&M. That's where Nicholas did his PhD. But what about like your undergrad?
Sure. Yeah. So as Evan mentioned, Nicholas Starvaggi. We both did our PhD at Texas A&M. Before that, I did my undergrad at Mount St. Mary's University, which is a small Catholic school on the East Coast in Maryland. So did my undergraduate degree in chemistry and biochemistry from 2017 to 2021, and then immediately jumped over to College Station to start my PhD with Emily Pentzer.
Mm-hmm. That's right. We were the Pentzer boys, if anyone ever asked. So Nicholas, you're doing some different stuff nowadays. What kind of I guess even while you were at A&M, or just in general, so what kind of scientist do you consider yourself?
Sure. So at A&M, I was definitely more of a materials scientist, and it's kind of funny, like the lines kind of start to blur when you get to materials science and engineering and chemistry and where all that fits in. These days, I would honestly consider myself kind of a jack of all trades kind of scientist because I don't really do one specific thing anymore. And even when I was a graduate student at A&M, my work was very interdisciplinary. So the work in the Pentzer lab very much exists at the intersection of organic synthesis, materials engineering, even a little bit of chemical engineering, depending on how you think about it. So there's really no one category that I think the work falls into. And a lot of the work that I did, again, very much at a crossroads of organic synthesis and materials engineering. So,
yeah, I would definitely say so, because there were some synthetic aspects of your stuff that you did, but it was also like very application focused, more like an engineer would
certainly.
be.
Yep.
And even the synthesis side we did, like that's why I always like to say to people is like, we do synthesis. We're not like true synthesis. We're like applied synthesis.
Right.
Like always synthesis with a goal in mind.
Sure. Yeah, certainly not fundamental synthesis.
Yeah, and there's nothing wrong with fundamental, pure synthesis. You need those people. That's just not what we were. But so you touched on it briefly. This research you did was at the interface of a lot of things. So kind of in your current work, what kind of research do you do? And then what was your research focusing on in your PhD at A&M?
Sure, so I'll start with my PhD at A&M. So my work really centered on developing new chemical strategies for microencapsulation. So the sort of anecdote that I always kind of tell people is I think about like a pill, right? A pill, some sort of medication, right? It's going to be the medication typically encapsulated in some kind of polymer film in order to protect it from water absorption or whatever. And what I did at A&M was I sort of developed new chemical routes to obtain those, but instead of at the macro scale, something that you could just see without the aid of a microscope, but several thousand times smaller, so the micro and the nano scale. So I developed new ways to encapsulate polyalpha olefins for example, like being able to sequester oils and for oil spill remediation, but also to encapsulate ionic liquids, which have very high free volume, and we use those for carbon capture. And it turns out when you encapsulate something like an ionic liquid, you increase its surface area, and then you enhance its ability to capture carbon dioxide. So my work really centered on developing ways to encapsulate these in polymer shells without contaminating the core so that you don't really mess with its performance for these specific applications.
Okay, and so I remember, I don't think you said it just now, but I remember you always talking about it in group meeting. It was templated Pickering emulsions?
Yes.
So could you, I never wanted to ask, but now that I have an audience, could you explain that?
Yeah, sure. So Pickering emulsions are basically how we go about encapsulating these fluids. And basically you take these solid or emulsions that are stabilized instead of by like small molecules like sodium dodecyl sulfate is your classic small molecule surfactant. But instead of those small molecules, we actually exchange those for particles like silica or clays or whatever. It turns out that those also do a great job at stabilizing emulsions because there's pretty high surface area of these particles and they overlap with each other and they form kind of a barrier at whatever liquid-liquid interface to get you these stable emulsions. And once you have these stable emulsions, you can manipulate various chemistries in order to develop like a polymer shell to form that's going to be maintained after you've finished your chemistry. And it helps to maintain whatever you're encapsulating inside this sort of shell. So a lot of the work that I did was figuring out new chemistries, new interfacial polymerization routes to get us to these microarchitectures that we could use for, again, these various applications.
Thank you for I finally feel confident enough to ask. So I guess you talked about your PhD. Are you able to talk about what you currently do, or?
Sure, I can speak to some degree. So I work for a materials engineering firm here in Austin, Texas, and we do a lot of contract work for the DoD, I guess now Department of War. So really the best way to sort of explain what I do is to say that the various agencies of the military, whether that be the Army or NAVAIR, NAVSEA, et cetera, they run into materials and engineering technicality like challenges all the time, right? Whether that's, a windscreen on one of their helicopters is getting a certain sort of damage and they need a way to repair that in the field. Or a warfighter who is going out on a mission, they need some sort of enhancement to the suit that they're wearing in order to extend the longevity of their mission. So what these agencies will do is whenever they encounter these types of problems, they'll put out a solicitation and they'll put them out to small businesses like mine. And my small business will see the problem that the Army or the Navy or whoever is having and will pitch a technical solution to their problem, essentially outlining, if we were to be given, let's say a contract for 6 months of work, this is the science that we would put forward in order to show feasibility in solving their problems. So it's competition-based. So a number of small businesses across the country will submit bids for this work. Typically, phase 1 type funding is 6 months. You're looking at probably about $250,000 for that 6 months of work. And then the DoW will select one or sometimes a couple of these companies, and they'll award them a 6-month contract to show proof of concept. And once that 6 months is done, typically, if the work goes well, you'll submit what's called a phase 2 proposal, and that's going to be for a much longer period. And that's more probably like 12 to 24 months of work. We're looking at like 1 to 2 million for that next period of performance. And at that point, it's really to develop the idea, right? So you've shown your feasibility, whether that's a materials solution or an engineering solution, whatever, in the phase 1. The Army, the Navy, whoever liked that, they liked what they saw. And now they're giving you a second contract to further develop the idea towards like a prototype. And then assuming that goes well, you'll be able to commercialize that, and you'll begin selling it to your customers at this point. Probably somebody in the military, but also commercially as well. So a lot of the work that I do is reviewing these solicitations as they come in every month and writing proposals, alongside my colleagues for funding that we think that we're competitive for. And sometimes we win, sometimes we lose. But then when these contracts actually come in, the second part of the work is actually doing the work, right? So whether that's doing it ourselves or subcontracting it out to universities or hiring technicians or undergraduate level researchers to actually do this work in our labs here so that we can show progress to our customers.
That's awesome, and I think that's so cool, and I don't think a lot of people really realize, because of maybe the politics of it or how they, war is a pretty bad thing. But there's so much research and just technology advancement that has been advanced by war, or not even war, but just in the pursuit of some military aim. And I even remember, being in the military myself, I remember when I was a young kid, there was a show I used to watch called Future Weapons. And it was, I guess it would have been like the phase 2 stuff that you were talking about. It was stuff that was just like, oh, way in the future, maybe we'll have this one day. But by the time I was in the Army, those were just things we had. And it was so crazy to that in my mind, like to see this on a TV show as a dream machination, or machination, however you say that. And then I'm in the Army and it's just a thing we have now.
Sure.
And it's insane that the rate at which technology progresses. That's sure. Cool that you're in that. Maybe you can get a TV show.
We'll see. Need a little bit more personality for that, maybe.
Yeah, no, you have plenty of personality, Nicholas. Don't sell yourself short. So you gave some you kind of answered my next question. This is some background on the field and its applications. You definitely hit that for your current research and work that you do. But can you give a little more background on the applications of, like I said, the emulsions work that you were doing at A&M?
Sure. So background meaning like technical background?
Not so much maybe technical background. I guess more you gave actually a pretty good background. Let's do more like the applications. I know you talked about a little bit like oil recovery and stuff like that.
So one of the ideas with some of the work that I was doing, right? So I developed a way to essentially encapsulate polyalpha olefin, right? Which is a high density, high molecular weight oil. And the idea there is if you have these capsules, these polymer capsules with your polyalpha olefin inside, again, there's not very much polyalpha olefin in each one of them, but the surface area is going to be really high. But the idea is that if you were to take this sort of shelf-stable powder and then place it into a vat of water that has been, let's say, spiked with, we would always use BTEX contaminants, so benzene, toluene, ethylbenzene, and xylene. Essentially what would happen is there's going to be a higher affinity within the capsule for these contaminants. So the polyalpha olefin capsules would actually draw out these contaminants from the water, and then you would get clean water. And essentially, if you think about it, right, you could sort of sequester these capsules once you've used them for your oil remediation, and then let's say put them in like a vacuum oven, right? And that'll pull off your contaminants, and essentially you've recycled them, so you can go ahead and use them again and again and again. So, yeah, and we talked a little bit about the whole carbon capture idea, but the idea being, again, just to hit on this one more time, is that these ionic liquids, they have very high free volume, right? So these cations and anions, they don't pack together really well, which means that there's just a lot of space in there, and that means that they're really great at dissolving gases, whether that's carbon dioxide or oxygen or nitrogen. A lot of these ionic liquids that the Pentzer lab has developed in collaboration with folks at the University of Kansas, among others, is that they're really great at solubilizing carbon dioxide. So we're able to sort of pull carbon dioxide out of the atmosphere, which has, as you can imagine, a lot of implications for carbon capture, essentially removing some CO2 in places that we might not necessarily want it. And then if we can sort of figure out a way from these capsules to pull the CO2 out of that, again, the ionic liquid within the capsules can be regenerated and they can be used again and again and again.
Yeah, almost like a closed loop kind of recycling type deal.
Yep.
All right, so thanks, Nicholas. You gave us some background on the application of that. Always good to know the application of our science. But now that we know like the applications and more background on this, what's something that you think people really like misunderstand about the field and its applications, whether that's just the larger scientific community or kind of just like the general population?
Sure. So as I mentioned, I do contract work for the DoD through an engineering firm here in Austin, Texas. And one of the things that I think people sort of get wrong about this field, and it's sort of manifested in often the responses that I get when I tell people what I can about the work that I do. And typically it's almost always followed up with, oh, so you develop chemical weapons, or something along those lines, right? Yeah. And that's certainly something that I'm sure happens, somewhere, someplace, but that's not what I do. And that's not what the majority of, let's say, contract chemists who do the type of work that I do work on. I personally, I think you have to be a very specific type of person to work on those things. You probably have to be very grounded in your ethics and whatnot. But I don't do any work on like chemical weapons, right? Again, I think you'd have to be, your ethics would have to be, really aligned or something for that to be the case. But I sort of think about the work that I'm doing is not so much as like advancing the, industrial military complex that maybe a lot of people sort of get wrong about, but really the work that I do, I think of it as making progress to keeping our service members safe, essentially developing the technology that at the end of the day is going to bring that person home to their families, right? And the example that I gave at the beginning was that, like if their helicopters or aircraft are getting a certain type of pit damage, right? Developing like a materials repair solution for that in the field so that they can repair that, essentially, that keeps them safe, right? If we're working on like CBRN suits or something along those lines, essentially making those suits more efficient to be able to, stay cooler for longer or something like that. Just again, to keep our service members safe and comfortable as, they're doing the important work that they're doing. So my role in that, again, is developing that technology to keep those people safe, is how I sort of think about it.
I think that's a good way to put it. And also, I think as as someone that's been in the military, and I did a tour in Afghanistan. People don't realize like how boring it is. And also that the technology that Western militaries have is so good because it's kind of boring. You don't think about it. It's just in the background doing its job. You think about like the technological marvel of what's like the stealth fighters. They have the paint and material that they say like it eats radar signature. That's not like a sexy thing, you know what I mean?
Because depending on who you talk to.
Well, depending on who you go.
I know some engineers who get really excited about that.
But people think of like, oh, we're making bombs, and someone is making bombs.
Sure.
Someone at General Dynamics probably.
Right.
But someone made a paint that eats radar.
Right. Yeah, I mean, it's really cool innovation that's happening, and it turns out that a lot of innovation for the Department of Defense, Department of War, is being done by small businesses across America, right? It's something like we get a lot of our funding through the SBIR and STTR acts. And those acts have essentially funded billions of dollars of research at small businesses since the acts were put into place in, I want to say, the 70s or something like that. So this work is being done by small businesses, again, for our customers, the largest one being the military.
Yeah, and I can say as someone who has, was the one carrying all this gear around in very hot conditions, something like that, like to someone might not say like, okay, you made it, so it's cooler. To me, that means a lot because I'm the one dragging this piece of whatever around or wearing this thing.
Yeah,
it means a lot. And people like they used to say ounces make pounds and pounds make. I'm gonna mess it up. Basically, like the ounces. I'm not gonna do it, but the ounces add up to pounds.
Stick to metric, right?
Yeah, pounds make you slower. The slower you are, the easier it is for someone to shoot you. Unfortunately, that's what it comes down to. So anywhere where you can cut weight is a good thing. So just stuff like that, and it's the most boring technological advancements that are like the best. And also as someone, so like when I was in the military, the people that were like my senior enlisted leaders, they were like in the military like when the war started. So like they were in like the invasions, or I had a platoon sergeant who was in Fallujah too. And they had what people don't realize is obviously we're developing technology, but whoever our adversary is, or whoever anyone's adversary is also trying to develop competing technology, even if they're considered like not a technologically advanced people. You could be surprised at what you can do with not that much. And so it's just a constant kind of game, for lack of a better word, of back and forth, and you'd be surprised at what it was. The big thing you saw about the war on terror was the IEDs, and eventually someone developed the MRAP, the mine resistant ambush protected vehicle, and they developed the hull in a way that it was meant to divert the blast, so that it was much more survivable against IEDs. And just something like that, like you said, people think of chemical gas, but chemical gas was also developed 100 years ago.
Right.
Also, it's wild. It's the same guy that the Haber-Bosch process. Is it Haber or Habner? I always mess it up. Haber, yeah, Haber-Bosch process. And what's wild is apparently on his deathbed, he's like, those are two of my greatest achievements, both of them put together.
Yeah, father of modern chemical warfare.
Yeah, chemical warfare and modern farming enrichment.
Yeah.
But no, that was very well put. So now we know about what you do. Let's talk about how you got into science. So how did you get involved in science?
Sure. So I think in my case, it was very much a phenomenon of, just take the next class sort of deal. So that probably started in high school. I knew that I liked, biology, I liked chemistry, I was doing well enough in math, and that was always the mentality, where it's like, if you find this interesting, just take the next class. So when I started at Mount St. Mary's, I was pretty sure that I wanted to go into chemistry. Wasn't entirely sure what kind of chemistry I'd be doing at some point, but flash forward 4 years later, I had done a lot of work as a research assistant in some of the labs there. I had added biochemistry as a secondary major. So I really got this really broad, sweeping education in STEM, really. And I was also, with that, able to do a lot of work as a research assistant, both at Mount St. Mary's, but also through various internships. I worked at Los Alamos National Lab out in New Mexico for a summer, and I also worked at Minerals Technologies, which is a mineral processing company up in the Scranton, Pennsylvania area. But through that, I found that I had a certain like lab dexterity. I was good with kind of working with my hands in the hood. And I enjoyed that sort of like analytical process. So that combined with again just sort of getting the next degree, it seemed like after Mount St. Mary's, kind of got me to where I am now.
That's good. So would you say just kind of something that just kind of happened like almost like slowly and then suddenly all at once, or it wasn't like you had some, I guess, like epiphany moment as a child or young adult or anything?
Yeah, I mean, I think I've always been curious about how things work. Sort of always asking why, right?
Mm-hmm.
Why is the sky blue? Why is a day 24 hours and not longer, not shorter? That sort of thing. I've always kind of wanted more than just the superficial sort of answers, and I think that is really what led me to wanting to do research at Mount St. Mary's, which really kicked off this trajectory of doing more and more advanced research to the point that, okay, now at Texas A&M University, essentially developing new chemistry, right? So things that people hadn't thought of before, being able to solve new types of problems through existing and unknown chemistry. And then now in my current position, again, sort of developing ideas towards certain applications. But all of that, comes back to kind of the basics, which is, stuff that I've studied for a while at this point.
Yeah, and so I like what you said, where it's just like this curiosity just led you to take the next class. So then in terms of a PhD, what led you to kind of apply that further? Be like, well, let me take like the next large step. Like, what made you want to pursue a PhD specifically?
Sure. So there were a number of reasons that I ended up making that decision. So that would have been that 2020 into 2021, and that was a very much different time than it is now, right? So we were kind of existing in the backdrop of the pandemic. I had just finished an internship. I mentioned that minerals processing company in Pennsylvania. Job prospects for entry-level chemists at that time weren't great. If I wanted to, I did have a position with that company that I could pursue if I wanted to, but for several personal reasons, I just decided that I didn't really want to jump into the workforce at that particular moment. And the idea of continuing my education through a PhD wasn't overwhelmingly repulsive. I really liked the idea of continuing to discover more, continuing to learn more advanced chemistry, and I was fine with not jumping into the workforce at that moment. So going to A&M, starting another 4 to 5 year academic journey, right? That made the most sense to me at the time.
That makes sense. It's similar, but not even similar. But anyone that was around during the pandemic, I know there was a lot of people that said I was going to apply to jobs, apply to grad school, see what's the best fit for me. But then the pandemic happened. There's no jobs. Well, I guess that made my decision.
Right. There was a lot of uncertainty regardless.
Yeah.
It was like, for a while we thought, this pandemic, is this going to shape the rest of our careers?
Yeah.
So it seemed at the time like, remaining in the bubble of academia, as it were, definitely seemed like kind of a safe bet because, no one really knew what was going to happen. So it just seemed like the right idea at the time, and it's certainly a decision I don't regret.
Yeah. So when you were, choosing, or I guess not even choosing to do the PhD yet, but at least feeling it out, how did you choose what schools you wanted to apply to, and then how did you eventually settle on A&M, and then I guess even further, how did you end up in the Pentzer group?
Sure. So yeah, I guess you've got 3 questions there, and I'll kind of answer them in order. So as far as deciding what schools to apply to, I really spent a lot of time my senior year of college just looking through the academic profiles of various schools. I had an idea of what research was interesting, but by and large, I simply read the first couple paragraphs on every faculty member's page, and I was like, it was either interesting to me or it wasn't. And I knew what kind of chemistry was kind of interesting, but actually reading the applications and seeing, okay, this is kind of interesting, maybe this isn't as interesting to me. But I applied to a school if they had, let's say, 3 to 4 faculty members that their work seemed interesting to me. I didn't really see a point in applying to a school if there was maybe 1 or 2, because there's not even a guarantee that that individual is accepting students, or even if they are accepting students, maybe it's a lab that you maybe don't want to join for a host of reasons. But essentially, you want to have options. So I developed a list. I want to say it was 7 or 8 schools. Based on, there was at least 4 or 5 faculty members where the work was interesting enough that it was worth another look, for example. So And then what was your second question?
Oh, it was how do you settle on A&M specifically?
Okay, that's a good point. So this was also very much, I want to say, a product of the time. So a lot of the schools that I applied to, being from Maryland, being from the Northeast area, a lot of them were in either New England or the Midwest. I think A&M was the only school, it was certainly the only school in Texas, and I think maybe the only school in the southern region of the United States. But at the time, and typically with graduate programs, PhDs in the natural sciences, if you're accepted into the program, typically they'll fly you out for a recruiting weekend, and they'll wine you and dine you, and they'll just sort of introduce you to what life is like in the department. Now, because a lot of counties were under COVID travel restrictions, a lot of the schools in the Northeast and even some in the Midwest weren't able to fly people out just because they had to, obey the restrictions that were coming down from the state, because that state is how they were getting their money to do this. So they were kind of cut off from a lot of that, what they would normally do. So essentially, in place of that, they would have these virtual recruiting weekends. And I remember sitting, in my dorm room, January of 2021, every single weekend, back to back for, I want to say close to 2 months. It was recruiting weekend after another. And it turns out that once you've seen, let's say 2 or 3 of these, they all start to sound the same, right? Because everybody can put their best foot forward over Zoom. I mean, that's not hard to do at all. But what you're sort of missing out on there is, that in-person experience to really kind of get this sense of what a school, what a culture is like. And at those in-person events, essentially what would happen is that you would have all of the official stuff put on by the school, but then you would get to talk with the graduate students kind of after hours, and they'd give you, the real spiel about what life is like as a student there. So all that is to say is, for our cohort, we didn't really get that at all. And I didn't feel super comfortable with the idea of, moving to a new state, moving to a new city, starting school at a brand new place, sight unseen. That wasn't something that I was willing to do. A lot of people did, and I'm sure a lot of people were successful in doing that. But just by virtue of where it was, Brazos Valley was slightly more open than a lot of the other counties, certainly a lot of the counties up north, again, due to a host of political reasons and whatnot. But even though they couldn't host a visit, an official visit, the graduate office said, if you can get yourself out here, if you buy a ticket, get yourself out here, we'll do everything in our power to just open the department to you, let you pair you with grad students, let you talk to the faculty members that you're interested in. And I just remember being so overwhelmed by the support and, as doing as much as they possibly could in a time when, we were so isolated. And that was kind of coming out of the pandemic it was almost like the light at the end of the tunnel. And I remember leaving and going back to Maryland, and it just felt like home. It felt like the right place to be. I had talked with, my future boss at that point, among a lot of other people that I'd be working with, pretty closely for the next couple of years. And I had this overwhelming sense of, peace in that decision. So I guess a couple of months later, I accepted the offer at A&M, and I was loading a U-Haul for College Station.
Yeah, that's what I remember that too. I didn't go in person, I don't think, till after I'd accepted, but I remember they had it was always like trivia or something, or something, and yeah, you got to actually talk to the grad students and that was a big thing and kind of shifting me towards A&M. So we know how you got to A&M. How'd you end up in the Pentzer lab?
Sure. So Emily was one of the individuals that I had talked to pretty extensively. So during the recruiting process, and then also really the summer before I started. Her work was interesting. I liked that it was very multifaceted. I liked that you weren't really pigeonholed into one area of chemistry. So there were a number of things that kind of stood out to me as, okay, this is interesting. I kind of want to learn more about this. But really what drove it home, beyond the fact that the culture of the group, seemed really positive, everyone seemed to get along, they hung out with each other outside of work, karaoke nights, all that sort of thing. But what really drove it home for me is that Emily was willing to work with me towards an NSF GRFP application. And so for those of you who aren't familiar with that, that's a fellowship through the National Science Foundation. It's a competitive fellowship where if you're awarded for that, then it's the National Science Foundation that's funding your PhD, not whatever, let's say, a grant that your PI gets, or certainly not teaching through the university, which is going to obviously take time away from doing that all-important research that's going to get you your PhD after 4 or 5 years. So I want to say Dr. Pentzer and I had a meeting in is probably July or maybe August of 2021. And essentially we sat down and I told her, hey, I really want to apply for this fellowship. Do you have some maybe ideas that we can start kicking around for a proposal? Because as part of that, you write a 2 or 3 page proposal as well as a personal statement. So we started kicking around ideas for that. And I pretty much soft committed to the group, and I think she was pretty aware that I was going to be joining the group because I was working on this proposal with her. So that ended up getting submitted in probably September, October. We didn't find the results until the following April, at which point I had already been in the group for 9 months at that point. But that's kind of more or less how I ended up in the group.
Yeah, I remember I talked to her pretty early on, and I ended up joining in the summer in like that 0 year, and I think that would help me decide like this is the right one for me.
Sure.
But and it kind of makes sense. You didn't join in the 0 year in the same sense, but you were already working with her.
Yeah.
And it gives you a sense because the fact she was able to work with you. I remember writing that GRFP. I hated that thing. I hate talking about myself. I hate writing those essays. But so shifting, I guess, more towards your PhD experience, what would you say your biggest challenge has been as a scientist?
Yeah, so I think, and this is probably something that a lot of people struggle with, is being able to embrace failure. And you might run into this, here and there as an undergraduate, whether that's a tough class or a research project that you're working on for some PI, and maybe it's not going all that well, but there's not maybe as much stake in that research as an undergraduate as when you're a graduate student, right? So when you're a graduate student, this was explained to me at the very beginning of my PhD, where it's like if you consider all of the knowledge that is contained in the world as a circle, right? And the work that you're going to be doing, right, is going to be right at the circumference of that. And essentially you're pushing that out, you're pushing the boundary of knowledge, right? You're developing and generating new knowledge. And that's kind of intimidating, right? And that means that you're going to fail, right? You're not going to be successful in your hypotheses and your theories. A lot of it, 90% of what you do, the experiments that you run, it's going to fail. It's not going to do what you expected. But being able to sort of think about that in a different way, right? Being, okay, this didn't tell me, this didn't happen the way that I thought it was going to happen, but what does it actually tell me? And how do we, realign our thinking and adjust, kind of going from there? So I think being able to treat failure differently is something that I had to, really develop early on, and really embracing it, because it's not going to work most of the time. 5 to 10% of the time that it does work, it's this light bulb moment and it's wonderful, and you publish a paper and then you get cited and your H-index goes up and it's wonderful. But most of the time, for weeks, months on end, you're going to be doing experiments that don't work. But being able to sort of see that as, okay, we've done that, what's next? Where do we go from here? It's not failure for the sake of failure. It's failure that adjusts, realigns your way of thinking.
Yeah, that's, I think, really good point. And that's something I know I struggled with. I always viewed it as like, oh wow, I messed that up. And it wasn't that I messed it up. I mean, sometimes there were things I just messed up. Sure. It wasn't that I messed it up, but it was just like, well, it just didn't do what we thought it would do.
Right.
And it's not anyone's fault. It's just the world.
Yeah.
And then we have to learn how to pivot. How do we? How Emily would say, well, what's the story now?
Yeah, what's the story?
What's the story now?
Good times.
Sound bites in my head of well, what's the story? So, what's a piece of advice that you wish someone had told you before you started your PhD?
Well, I mean, certainly, know that you're going to fail a lot. Knowing that, I kind of started my PhD in very much a perfectionist kind of mindset. And I think that's probably, a vantage point that a lot of us come into science with, because let's say, you've done your 4 years of your undergraduate, and if you're kind of at that top 10%, you're going to be really ambitious. You're going to be doing trying to make all A's and all of that, and you've got this sort of perfectionist mindset that I have to like get everything right 100% of the time. And that will burn you out so quickly in a PhD, because it's not going to go perfectly 100% of the time. It might not even go perfectly 90% of the time. So sort of coming out of that, realizing when it's time to maybe throw in the towel with something, and maybe start to think about things in a different way. So I think that for sure, and then also just patience, right? Patience with yourself, patience with your lab mates, patience with your PI, because it's, especially coming into it, you're going to have two different ways of doing things, and ideally by the end you've developed this sort of new way of doing things together that maybe bridges your PI's approach and maybe your own sort of creative approach that you kind of come into the group with. But those are going to be two disparate things at the very beginning. So eventually having those kind of come together, it's a learning process, and it requires a lot of patience. Certainly with your PI, with your lab members, there's going to be friction, right? There always is. No one gets through, a PhD without, some days where they just want to go home and just completely throw in the towel, right? That happens to all of us. But being able to kind of push through that, make it to the next day, kind of reset, and just kind of get back to it is, it's important.
Yeah, I would agree. I think especially, like you said, touched on, like, people are high performers. Like, I almost likened it, like I was almost always likened it to like almost being drafted. Like, you were the best at your school, maybe not the best, but you were like the top 10% or something at your school. Now you're coming to an arena where everybody was the top 10% at their school. Yeah. And you're used to just being the top 10%. Yeah. And it's like, they're not your competition, but like, for lack of a better term, the competition's harder now. It's another level.
Right. And it was explained to me as, you're no longer a big fish in a little pond. I mean, you might be a big fish, but you're a big fish in the ocean now.
Yeah, with a lot of other
other big fish, yeah.
Yeah. So, all right, moving on to something a little happier. What's your favorite part of being a scientist, or what was your favorite grad school moment?
Sure. So I can address both of those. I think as for being a scientist, the best part about that, I think, is that my work, my day-to-day life is very dynamic. There's no 2 days that are really identical. So I feel like I'm not doing a lot of process type stuff where maybe I'm doing the same thing every day. Like, there's no 8 hours of my workday that are identical to the 8 hours of the next workday. And that's something that I've really wanted all along. So in part of that decision to go from undergraduate to grad school, I wanted certainly not having a ceiling as far as salary. That's a great thing too, a good reason, but also just knowing that as an entry-level chemist, you're probably going to be doing a lot of technician type work, and that's something that it's important, right? We need to have technicians and entry-level chemists out there doing a lot of good work that they do, but I knew that at some point I was kind of want to get away from that. I wanted to be involved more in the decision-making processes and eventually get maybe more into management. So just knowing that, with a graduate degree, the options are kind of endless, right? So no 2 days are exactly alike, right now, and there's also the opportunity to kind of venture into, project management if that's something that I want to do, or to get, more hardcore into chemistry, or maybe to pursue a position in academia, right? There's all of these different things that you can do with a PhD that you might not be able to do with, just an entry-level, a bachelor's degree. Now, speaking of happy moments at A&M, there were so many, wonderful, memories. I'm sure Evan's probably talked about these before, but we had such a great culture at A&M. Especially when we were there, 2021 to 2025. One of the things that I will always remember about just being a student there was the people. The people in the department, not just the people in our cohort, but students above, below us, the faculty, the members of the graduate office, just really wonderful people to be around. And I tell people that the first 6 months of me being there, every interaction that I had with my students, so the engineers that I was teaching in General Chemistry 1, to my lab mates, to my PI. It was like sort of this living validation that like this was the right decision, like this was the right place to be. And at A&M, just being a big SEC school, we spent a lot of times at football games and tailgates and at Northgate, right? So it was just this wonderful place to really spend a PhD. And I tell people that like I'm very fortunate because I had like this small school experience at Mount St. Mary's, like a school of like 2,000 people. Sports wasn't really that big of a deal for us, but then going and having essentially the experience on the other end of the spectrum of being, at a really big school, but in a relatively mid-sized department where you still kind of got to know everybody, the faculty, the students, and you spent time with them. And we enjoyed spending time with each other, outside of lab, whether that was like at a barbecue or a tailgate or at, Emily's place singing karaoke. A lot of good memories for sure. We had a lot of fun.
Yeah, those are some really good memories. That was one thing I always remembered about A&M is just the department seemed to get along, obviously you're not going to get along with everyone.
Sure.
And I can't say that I knew every single person in the department, but it felt like I did. And we were always
the same people. Yeah.
Yeah, especially I always liked the tailgates. I was a big fan of the tailgates. I maybe put a little bit of, or maybe a lot of work into those tailgates, even when I wasn't on the planning committees or anything. I love a good tailgate. So if someone sees this and they think they maybe want to look into a PhD, what's a skill you think they should cultivate? You've kind of already talked about this thing of be okay with failure. You have to have longevity, look at the long game. It's not a sprint. But what's another skill you think they should cultivate?
Sure, I think good communication is really important because you sort of, from the outside looking in, it's like, okay, you're going to be doing a lot of work kind of on your own. And that's true. You're going to be doing a lot of hands-on stuff. You're going to be either developing new methods or learning new methods and spending a lot of time like in the hood or at a glove box or whatever. But at the same time, you're having to develop these other skills as well. Like you're going to have to develop presentation skills and public speaking skills and mentoring skills. So just knowing that it's not really just you doing the work that it is to get your PhD, the work that's going to ultimately be in your dissertation. But there's also a big component of it that is being able to communicate science. And that's something that I struggled with, quite a bit the first year is developing confidence and being able to speak with confidence, whether that was presenting something at group meeting and eventually presenting at like ACS, several years later. But that's the sort of thing that you might not think about as playing that big of a role because maybe you've done presentations in undergraduate, every now and again, maybe it's at the end of a course or something like that. But in graduate school, you're presenting, at least for me, it seemed like at least every week, because if it's not in group meeting, then maybe it's in a subgroup presentation, or maybe you're working with a number of other universities on a shared project or a shared NSF center. So you're having to present your work to other people who need to understand your data so that they can make progress, on their parts of the project. So being able to, deliver results, in a quickly, concisely, without, kind of spilling all over your words and whatnot, that's something that, I don't know that anyone has really mastered it before coming into graduate school because they certainly aren't doing it probably at the volume that you are once you're in graduate school. But just knowing that if you can hone those skills in, in undergraduate, that's something that's going to serve you so well because you're going to be doing a lot of it for sure.
Yeah, I will definitely say my presentations were kind of garbage when I first got to A&M. I can admit that if I were to look at I remember when we did our what was it the seminar we had to give?
Sure.
If I took that presentation and showed it someone to one of my ACS talks or my final defense, they probably wouldn't think it's the same person unless other than the same names on there.
No, it's the same thing for me. I mean, it's some of those presentations that I gave early on. I would look over them several years later. I'd be like, oh my gosh, who did this?
I can't believe. And especially the confidence thing when you talk about it. So something I ran into is there are definitely some things I should have made sure I had a little bit more background on because some of my work touched into electrochemistry, and at first I was like, oh, well, I'm not the one that does it. I don't need to know that much about it. But then, I got caught up a couple times where I got asked questions about electrochemistry that weren't, satisfactory to my standard or the standard of the person who's asking. Then there was other times where I knew exactly what I was talking about, but I didn't have as much confidence. And so it sounded like I didn't know what I was talking about, or what I was just saying was just wrong, and it led to someone kind of
almost as bad, right?
Yeah, and someone just trying to latch onto that, a shark smelling blood in the water.
Yeah. Classic academic.
Yeah, and then trying to trip me up on it, and then I was fine because I did fundamentally know my stuff when it came to synthesis, but I had to dig my way out of that hole then. Whereas if I just said, actually no, it's this, or just spoke with confidence to the point that they didn't even question it. So I think that's a really good point, and no one's ever brought that up yet. So I want to switch gears a little bit. So you also teach, correctly?
I do.
Not correctly? Correct.
Yeah, I do, yes.
So you teach general chemistry, right?
I do, yes.
So what do you like about teaching? Do you like teaching?
I do, yeah. So I'll say that we touched on this briefly, right? I received a fellowship through the National Science Foundation in the first year of my Ph.D. So at A&M, graduate students are required to teach 1 full year, so 2 academic semesters as part of the Ph.D. Now, many students will teach more than that. Some of them might teach for 2, 3, 4 years, however much is needed so that their tuition can be covered. If, let's say, their PI doesn't have RIs or research funding RF for them. Now, in my case, when you have the NSF GRFP, that bars you from teaching. It wasn't always the case, but it is the case now. And the mentality there is that if you have this funding from the National Science Foundation for you to do research, then you should be doing research. And a lot of people in the past would kind of stack that on top of teaching so that they could be making a little better than a postdoc salary or something like that. But that's not the point, right? The whole spirit of the NSF GRFP is that it's funding you to do research. It's alleviating a lot of those burdens associated with teaching. So I bring all of that up because I got to teach a little bit at Texas A&M. I taught General Chemistry 1 lab in the fall of my first semester, and then I kind of switched gears and taught Organic Chemistry 2 lab the second semester, so completely different class. But then after that, I didn't teach at all. I loved teaching. I really enjoyed being able to engage with the students at A&M, seeing them kind of grow and learn. That was something that, honestly, the first year of graduate school I think was the toughest for me by and large. And there were some weeks where, walking out of lab or out of the teaching lab was the best part of my day. Being the time spent with my students, that was, for many weeks, that was the highlight. So I wasn't able to sort of do that very much in the rest of my graduate career because of the fellowship. I was engaged in research in Emily's lab. So when I saw, I think I was browsing through LinkedIn last summer, and I saw a job posting for an adjunct chemistry professor at Austin Community College. So it's the local community college here in Austin. It's actually one of the largest community college districts in the country. I think it's 6th or 7th or something like that. But all that is to say that is they operate 11 different campuses in the greater Central Texas area. Most of them are kind of in the Austin area, but some of them kind of go, I believe, as far south as New Braunfels area. So it's a very large district. There's a number of campuses, and of course, there's going to be a lot of opportunities for general chemistry and organic chemistry. A lot of community college students need to take this if they're, for example, going into or planning to go into the medical school route or the dental school route. These are all prerequisites and material that's going to be on the MCAT, for example. So I sort of saw this as an opportunity to maybe remain engaged with academia at the community college level, even now as an industry scientist. So this past spring of 2026, I taught my first course. I taught an evening class, so I work during the day, typically 7 to 3:30-ish. And then Tuesday, Thursdays, this past spring, I taught a lecture. So the lecture met twice a week, and then there was a lab component as well that was in the evenings on Thursday. So it was an evening class. You had a lot of students that maybe had a full-time job, and it was easier for them to just continue their education in the evenings, which is primarily what community college serves, is adults that maybe they finished high school or maybe they didn't finish high school, and they're looking for a way to sort of continue their education. So I taught a Tuesday, Thursday General Chemistry 1 course this past spring, and yeah, it was a great experience, and I'll be continuing that again this fall.
It's awesome. I'm glad to hear that. I'm glad I always knew I didn't want to teach, but I will say at A&M, the teaching was actually like a positive experience for me. In like a very healthy way, it reinforced like, no, this isn't what I want to do as a career. But I actually did kind of enjoy it, especially like the mentorship aspect, like you said, watching your students grow. Because a couple of kids I had for both semesters, or to watch like a kid that struggling turn their grade around, and some of them I've still stayed in touch with. Or one of them, my student David, he ended up doing research with us, and so now he's getting his Ph.D. He's starting at I want to say it's UMD. So
College Park. Yeah, very good.
Yeah, so I saw him from OChem 1 to, I guess no, I got him for OChem 2, but OChem 2, now he's starting his PhD.
Yeah, good for him.
So on my teaching channel, I always get questions about like, oh, I'm nervous, what do I need to study beforehand, or what do people struggle with the most? And I can talk about OChem, but for Gen Chem, what's something that you see students struggle with the most?
Sure. So I mean, there's a number of things that I think that students struggle with general chemistry. But I think the biggest thing is, well, I'll talk about two things. The biggest thing is that general chemistry, in many cases, it's probably the first course where a student kind of has to retain all of the knowledge from the very first class all the way through the final class. Essentially, everything builds upon itself. And in teaching this course, I actually gained a better appreciation for why the course is set up the way that it is. And it turns out that general chemistry, if you take it at one place or another, it's more or less going to be the same content. And what's interesting is it's more or less going to be presented in the same order. And that's completely by design. So any general chemistry 1 course you take, whether it's at Texas A&M or Mount St. Mary's University or University of Nebraska or Montana or wherever, you're always going to begin with a discussion on measurement and units and significant figures and being able to convert from inches to centimeters, because in science we've developed all of these different measurement systems, so being able to convert between one or another is so absolutely fundamental. And you'd think, okay, once you've mastered that, maybe we can leave it and move on. Well, it turns out that all of the math that you're going to be doing throughout the entire course, I don't think there was a single exercise that we did that didn't involve a unit conversion at some point, whether it was converting amounts of chemicals, whether that's like in moles, to something a little bit more practical, like grams or kilograms, something like that. So things that you maybe don't necessarily think about as being important are actually very fundamental. And I think students, if they're sort of used to a course-based structure where let's say they do a unit and then they have their exam and then that's the last that they're going to see of it until the final, and then they begin their second unit. Well, general chemistry isn't set up that way. It's sort of set up in the sense that you sort of start with very simple concepts, but those concepts start to snowball, right? And it's very easy to sort of fall behind if you're not paying attention to the material. It's very easy to say, well, I don't really understand that, but I'm not going to worry about it. I'm just going to go to class and maybe hopefully get the next thing. And unfortunately, it doesn't work that way, because if you don't understand what was taught on a Tuesday, there's a good chance that the material on Thursday is going to not only incorporate that, but build on it and become more complex. So my advice to students is, remain on top of your lecture notes. Don't, skimp on that. Go to class. If you need to, retrace your lecture notes after doing the class just to reintegrate it into your brain, and maybe look at those notes again before the next class, just so that maybe what to expect kind of going in. And then sort of the second thing that that I saw students struggling with, and it's actually something that in a way I kind of struggled with as their instructor. And this is very much a thing that is intrinsic to general chemistry. But general chemistry as a course is meant to be this broad, like brushstrokes overview of the field. Now, chemistry is such a vast, it is the central science. It's such a vast, covers such a vast area, so many different topics, that it's tough to spend a lot of time on any given topic because there's just so much. And what that means is that you don't spend nearly as much time with certain concepts as is really required. So when I was an undergraduate, I was always told that some things that are presented in general chemistry is an oversimplification. Maybe it applies to a very specific set of molecules or systems or whatever, but what you're being told, often there's a number of assumptions kind of rolled into that. And then with that, there's a unit on quantum mechanics, right? Quantum mechanics, it's so fundamental to our understanding of chemistry, but as an undergraduate student who, maybe this is your first chemistry course, you don't have the background to really understand the depth and the complexity. So, we're throwing things around like principal quantum numbers and angular quantum numbers, and all of these come out of like the Schrodinger equation, but when you're in the moment taking this course, you haven't had physics, you haven't had calculus. So a lot of it is, this is the way that it is, and you're just gonna have to take my word for it right now. If you take a couple of other courses in the future, if you take, P-Chem and analytical chem, like this will all begin to sort of make more sense after you have the math background to understand polar coordinates and spherical coordinates and understand how these systems actually exist in 3D space. But at the very beginning, at the general chemistry level, you just don't have that background. So unfortunately, you have to make a lot of assumptions and just sort of present things that unfortunately aren't going to make a lot of sense. And that was difficult for me as an instructor because, as I'm sitting preparing my lectures for the next class, I'm like, what is the best way for me to explain this to someone who has absolutely no background in advanced mathematics or physics or something like that. And it's tough. It's not easy. There's been people who have studied this for much longer than I have, who have developed all of these wonderful resources on YouTube that I constantly point my students toward, where it's like, okay, if you didn't quite understand the way that I'm presenting it or the book is presenting it, go watch these videos because these are going to do a much better job, or maybe just a different way of explaining it than I can. And being at the level that you're at right now, you don't have really the math to understand this, but this is maybe the best way that you can understand this right now. So just being aware of your resources, I guess, is another really important thing. So.
Yeah, I can see how that would be tough because like Gen Chem is like mile wide, inch deep to the field of chemistry.
Yeah, cowboy chem as we call it at A&M.
I always thought cowboy chem was chem for the ag students.
I mean, it's probably a number of things.
But yeah, and like looking back, I remember like taking Gen Chem thinking like, I'm so smart, I'm learning about all this, and then you learn it's wrong. But even in organic chemistry, there's like that, and I have to, even when I do my videos, I have to sometimes put some qualifying language on things, and it's be like, well, when we learn this in undergraduate chemistry, we make the assumptions that.
Right.
Because one, that's something that I'm kind of forgetting, but also there's always going to be someone in the comments that's like, well, actually, and it's like, okay, guy.
Calm down.
But it is something that I've even noticed I have to be aware of, like how I'm phrasing it or presenting it to a student, because they're just going to take it as what I said and not realizing that like, hey, we're making the assumption at this level, of like, say for like NMR, usually for NMR, like n+1 multiplicity, we're making the assumption that everything's coupling equally.
Right.
It probably isn't.
It probably isn't.
But for right now, for you to understand just the concept of this, that's what we're working with. And so that's really good. And now before we end, I want to ask one last question. So right now, I've been getting a ton of questions from students that are about to take organic chemistry, and they want to know, what should I guess I'll ask two parts. So what should I study from general chemistry that I'm going to need in organic chemistry? And then the second one is they hear, well, I've heard if you do good in general chemistry, you're going to do bad in organic chemistry, or vice versa, because they're so different. So I guess your first one, I guess I'll phrase a little. First one, what would you say to the students out there that took Gen Chem and about to take organic chemistry? What do they need to maybe sharpen up on, brush up on from Gen Chem for OChem? And then how do you feel on that whole kind of, well, there's such different chemistries, you can't be good at one and good at the other?
Sure. Well, I'll answer your second question first. I don't agree with that mentality at all, because there are plenty of us that did fine in general chemistry and did fine in organic chemistry. They're different in the sense that general chemistry, at least as it is taught these days, it's very math heavy. And by math heavy, it's typically algebra based. You don't get into the calculus until physics or whatever. So contrast that with organic chemistry, very little math, at least from what I can recall. I mean, maybe you do a little bit of math with like NMR, but it's very basic sort of stuff. So if you're able to understand how equations work and being able to kind of plug and chug different values and being able to retain different constants in your head or how to use them, general chemistry is going to be a breeze for you. Now, organic chemistry, if you have a harder time visualizing 3D structures and the way that electrons move and all of this, if you can kind of see things in your head a little bit, maybe organic chemistry is going to be a little bit easier. But so much of organic chemistry is you just have to draw it out, right? Like are the electrons moving in the direction that they should be moving based on the charges and whatnot. So you'd want to I would recommend, for someone who's studying organic chemistry, get very comfortable with pulling out a whiteboard and just, practicing this chemistry on the whiteboard, because it's like, unless you can see it all in your head, which 99% of us can't do, you're just going to be, left with, drawing these mechanisms out, and it takes practice. Now, to answer your first question, brushing up from general chemistry to organic chemistry. So it's interesting that, general chemistry is a required prerequisite for organic chemistry. It's the first chemistry course that anyone's ever going to take. And this might be a little bit of a controversial opinion here, but there's not much from general chemistry that carries over to organic chemistry, because with organic chemistry, now you're focusing on something much more specific. So you're focusing on the chemistry of carbon, and as it relates to typically oxygen and hydrogen and other hydrocarbons. Versus general chemistry, you're just sort of being presented, as much as you can of, as much as, is out there. So you're going to be seeing a lot of like oversimplifications as far as, math, but really they're trying to just, you're drinking out of the fire hose with general chemistry. Organic chemistry, you start to become much more, specialized. So I think really the best thing that somebody can take away from general chemistry and apply to their organic chemistry is, knowing how best to learn, I think is the most important thing, right? Because, for many people, I feel like general chemistry is the first course where you're having to do some serious, teaching yourself how to learn. And that's going to carry over, for the rest of your career in chemistry, I would argue. So if you can teach yourself the best way it is for you to learn and retain material and to build on material, and the best way to study, that's what's going to serve you the best. Honestly, I think that's probably more important than any specific concept, because, in general chemistry, we spend a lot of time on, for example, like pressure, the laws of pressure and gases and constants and all of this. But in organic chemistry, I don't think that comes up a single time. Not to say that it's not important, but what's important is, being able to make those connections, right? Understanding how equations work, how they're applied. That's what's going to serve you well in organic chemistry. Because if I remember correctly, it's like first semester organic chemistry, you're kind of learning all of the rules of how things work and what interacts with what, etc. And then in the second half, you're really playing the game, right? Using those rules that you've kind of developed and learned about to actually understand systems that are now more complex. So learning how to learn, I think that's something that many of my students had to develop kind of in a relatively quick time frame, but it's something that, if you're doing that throughout your the process of that first chemistry course, that's going to serve you well, not only for other chemistry courses, but for other, advanced courses in STEM that you'll take. So.
Yeah, I think that's good, because usually when people ask me, I tell them there's really not much that carries over. I was like, if you really want something, like, I guess brush up on like just generally the concept of bonding, like your octet rule.
Sure, yeah.
Yeah, like Lewis dot structures and...
Yeah, I guess Lewis dot structures, that's a good thing.
I think that's really it. It's like Lewis dot structures, and then even that's just going to go to bond line notation. But just like, octet rule, just what an acid and a base is.
Right, yeah,
and then, like,
don't make 5 bonds to your carbon.
But like there's almost no math in organic chemistry, which is kind of why I like it.
Right.
But I think you're right, though. The difference really is some people really struggle, and I see this a lot with people I work with. Some people really struggle with visualizing molecules, and that's what organic chemistry is it's all about structure. How does stuff relate to each other in 3D?
Sure.
And so if you struggle with that, doesn't mean you can't do well. You can still totally get an A, but you're gonna have to work a little harder than maybe the person that just sees it in their mind's eye. But I will say that almost all the answers in organic chemistry come back down to, oh, the electron density, or oh, sterics.
Yeah.
In a very broad, general sense.
Sure, yeah.
But yeah, well, Nicholas, this has been great. Thanks so much, man.
My pleasure.
Everybody, that was Dr. Nicholas Starvaggi.
Thank you for having me.